Let's finish up this problem about basketball player making foul shots to illustrate aspects of the binomial probability model, or also known as the binomial distribution. We've looked at various questions, and the big thing we've got is this master formula now, which is the n choose x, p to the x, q to the n minus x. This master formula. Okay, so let's look at that. Let's look at that as a master formula because I haven't written it down quite yet. So probability of exactly x successes in n trials, and where p is the probability of success on each trial and q is 1 minus p, it's the probability of failure on each trial, okay, then that's going to be this kind of expression. It's going to be the total number, and then I have to choose x slots for the wins are going to be, where the successes are going to be, then times the probability of a success times that x to the x power, and then q to the n minus x. Okay, that is a super important formula. And it's going to be the exact formula for the probability of exactly x successes in n trials. Now, to be honest, we're going to be looking at a lot of cases where we actually, where these numbers would get pretty unmanageable, and it turns out that the normal distribution, the normal model, comes to the rescue. But it's still really fundamental importance. Now, that's great to have this master formula, and that is what we use basically in this example, making exactly 7 out of 10 foul shots. But what if we have some other question? There's going to be related questions. What about at least 7 out of 10? Okay. Well, that's a little different question. Okay. So that's the probability. Let's put it in non-math mode. That's 7. Oops. I still want non-math mode. Sorry. Probability 7 out of 10 plus the probability of 8 plus the probability of 9 plus the probability of 10. Here we're using the disjoint, the summation rule. If he makes exactly 7 successes, that's definitely disjoint or mutually exclusive with making exactly 8 or exactly 9 or exactly 10. These are all the ways you can make at least 7 out of 10. Okay, so that's not too unwieldy. Let's put it back in math mode. And we can use this formula 4 times. It's all going to be out of 10. Okay, I need to do the 7, which we just did. And then that's going to be a 3. Okay, and then of course in this problem this is the 0.70, and this is 1 minus that. It's always 1 minus that, 0.30. Okay, then plus, let's actually do plus down here, and then it's going to be a very similar expression, but with 4 different numbers. And let's copy that whole thing. Okay, then 10 choose 8, 10 choose 9, 10 choose 10. And then this is going to be 8 and 2, and 9 and 1, and 10 and 0. You can see it's getting a little clunky even though there's only 4 possibilities, and that's going to be very important for part G at the end here. Okay, so these we can all calculate. Certainly you can do this on the calculator. Remember the alternate notation for 10 choose 7 is it's a 10 choose 10C7 like that, and it's in the math perb menu. Maybe I'll do one explicit on the calculator, but I don't want to start up the document camera right now. Okay, so we could just have the computer do all this, but let me illustrate again. We already have the 10C7, so let's just put that in here. Just want to illustrate one more time how it works by hand. Now 10 and 8, I want to illustrate this kind of massive cancellation property we have again. 10 times 9 times 8 times 7 times 6. Hopefully I won't skip 7 again. Let's see. Times 4 times 3. Okay, you put down 8 numbers up here, and then there's 8 numbers on the bottom to be multiplied as well. Remember, the 8 numbers on top just tell us how many ways we could count these with order, and then we correct for that overcounting by grouping them into all the different ways that the different orders give us. There's a lot of cancellations here. Notice everything from the 8 down to the 3 cancels out. Okay, and I want to illustrate something. That's the same thing I would get if I said 10 choose 2. That's two numbers starting from 10 going down, divided by 2 factorial. Okay, so that's a general property, and it's very simple. If I have 10 slots and I want to choose 8 of them, what I could do is I could be clever and just choose the 2 that aren't the successes. I could choose the failures instead of the successes. It's the same information. So in fact, anytime you have something like this, I could have rewritten it as 10 choose 3, and 10 choose 2, and 10 choose 1, and 10 choose 0. Ooh, that sounds weird. Choose 0 things? Well, there's only one way that could be all successes and no failures, so that's always going to be 1. Okay, so that's very nice and simple. So whenever you have like a choose number and this one's bigger than halfway to the complete number of slots, you can always just subtract it from the complete number and get an easier calculation. Okay, so this, let's go back to 10 choose 2 by hand. That's just 45, so that's not that unmanageable. Okay, now these guys, of course, we'd want to do with the calculator. Let me just put them in real quick. We'll do that numerically in a minute. Now 10 choose 1, that's very simple. That's just how many ways to choose one slot to be the success and everything else to be the failure. Okay, or in this case, actually, it's how many ways to choose one to be the failure and everything else to be success, because I did that trick about switching successes and failures. Well, that's just 10. Okay, so that's another very simple thing about these coefficients called binomial coefficients or choose coefficients. If I choose 10 things or 0 things out of 10, it's 1. If I choose 9 things or 1 things out of 10, it's just going to be 10. The other ones are the more complicated numbers. Okay, so that's 10 times this guy. Okay, and then plus 1 times this guy. Okay, so finally, that is something we can calculate. It's probably not going to put it in the right place, but let's do it anyway. Okay, 23347. So 0.26683 plus 0.23347 plus this guy 0.12106 plus, I don't need the 1 times now, do I? And then, that's scientific notation, but it's just 0.28248. Okay. And that, let's add that all up. Okay, total, it's actually a pretty good chance. 64961 is about 65%. Okay, so let's do a reality check. He's remember, he's a 70% free throw shooter. What's the chance that he makes kind of how much we'd expect, 7 out of 10 or more, 65%? Pretty good. If you bet on him getting what you'd expect or more, it's more than 50%. That makes a lot of sense. Notice, though, the contributions are rather different. It's the biggest one, not surprisingly, is about how much we'd expect, the 70%. Pretty close to get 80%, actually, to get 8 out of 10. Not about half as much to get 9 out of 10. And pretty unlikely, it drops quite a bit, pretty unlikely to get perfect, because he's only a 70% shooter. You'd bet that he'd miss at least 1. Okay. Alrighty, so speaking of which, let's look at this last one. He makes at least 1 out of 10. So I want to contrast that with this one. Here, it was a fair amount of work, but it was still doable to break it up into a bunch of different cases, disjoint cases. Here it would be a real pain in the butt to do that. We'd have to break it up into he makes exactly 1, or exactly 2, or exactly 3, or exactly 4, or exactly 5, and add them all up. So we'd have to take this and add up the 1, 2, 3, 4, 5, 6. But there's a much better way. Remember, at least 1, that should be a hint that we could use complement. Okay, so another way to say this is it is not the case that he makes no shots. Okay, or in other words, it is not the case, that's going to be a 1 minus, because it's a complement, that he fails the first and fails the second and ... Okay, a bunch of fails. Okay, and that's actually a very special case of the binomial. It's fail, 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 fail. Okay, you don't even really need to use the binomial though. Probability of fail, 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 fail is just going to be, that's just going to be our back to our basic independence multiplication rule. Even though it is a special case of the binomial, it's just going to be the chance of failing once to the 10th power. Okay. And so the probability of at least, or makes at least 1, is going to be 1 minus. So this is really something we actually have done before, but I just want to remind you. And it does fit into this basic case of the binomial. Here, if we wanted to be overly fancy, we could say this is 10 choose 0 for no successes times 0.70 to the 0th power, because there's no times when he actually succeeds, times the 0.30 to the 10th power. It fits the pattern, but it's kind of silly because this is just 1. There's only one way for them to all be F's, and I don't get any factors 0.70 because he never wins, he never succeeds, and then it's all factors 0.30. And then we'll just evaluate that. Pretty darn probable, 0.99999. Very, very likely. It would be really, really sort of impressively bad if he's a pretty good free throw shooter and he does not make any of his shots. So beware of this. The at least one kind of condition. At least two you could also do as a complement as well. It's a bit of an art as to when do you use the complement and when do you not. Just think about which one is the more easy calculation. Always think about availing yourself of the possibility to use the complement rule. Okay.